Hi, everyone. So at the end of last video, we came to the point of realizing that we have to apply 4 remaining boundary conditions in order to solve for the 4 unknowns. I decided to make that calculation optional. It's pretty technical, and I'm under the impression that some students would find it really difficult to follow. And I'm not sure if there's a lot to gain from that for them. If you're a physics major, you should see it because you will probably see it again. But I decided to make that calculation optional. What we're doing is already so far out of the bounds of what you're used to that it might be overwhelming. And so I will just skip that. I will have an optional video where I go through the math. So if you want to see the details, you can see the details. But at this point, I will just state the upshot of that calculation. Now, I said that there are 4 equations for 4 unknowns, the 4 coefficients, A, B, I think D and E, something like that. But in the process of solving them, we will also come up with a condition on the wave number of the wiggles in region 2. So this is where I'm going to pick up. I'm going to state the result of all that algebra so we can get to the analysis, and I can tell you how to use it to solve problems, because you will have a homework problem involving that. Okay? So the upshot of applying the 4 remaining boundary conditions are the following pair of equations for K. It turns out that those conditions actually, what they really do is they place restriction on the wave number of the sinusoidal part of the solution inside the well. Let me do the math, and then I will explain. I will try to give a little bit of physical intuition. Why is it that a condition pops out, condition on the K pops out? Why is K restricted? What prevents K from having an arbitrary value? Let me do the math first. So what are these equations? The first equation is the following. And the second equation is and the right hand side is the same. So bear with me, don't panic. I want to remind you what is K, right? And I want to remind you what is D. So not remind you, but state D, the script D is actually, it's a bunch of parameters, it's a bunch of constants. It's a bunch of crap, basically. So it's 2m u naught over h bar squared, all taken square root. A bunch of constants. And k, well, that's just 2 pi over the wave length, right? So it's a wave number in region 2. So remember what happened is we had a well. What are these constants? This was U naught, the depth of the well. This was L, the width of the well. And inside, we had sinusoidal solution, right, that matched up to a decaying bits outside, but inside it has some kind of a sinusoidal solution with wave number lambda. So that's what all these numbers mean. I want to stress upon you the following thing. This looks scary. I know, it's beyond what you've seen. D and L, script D and L, they're just a bunch of numbers. It's a number. So this is some number, just like 17. L is also a number. These are pairs of equations for K. The only unknown here is K. So the allowed wave number of the wiggles inside the well are given by solution to these equations. Before I tell you how to find those Ks, I want to do a little bit of simplification. The simplification is the following, that we can clean it up. We can clean it up. Rather than having to deal with K, I can nickname KL, I can call it X. We're really solving for K. L is just a number that gets tagged along. So we can call KL, we can call it X. It's going to be simpler. And DL is just some kind of a number, like 17. So let me rewrite these things neater with X instead. It's just going to look a little bit easier on the eye. That's all. So let me do that. Okay, so I rewrote that in terms of X, a little neater, a little more compact. And don't be scared of this DL, it's just a number. D is a number. 2 times m times u naught over h bar squared taken square root is going to be some shebang, some number. And L is some number. So DL is some number. So in your next homework, you're given a square well, you're given u naught, you're given the L, and you need to come, and you're given the mass of the particle that's inside the well. And out of that, you will compute a bunch of, you compute this whole D, it's going to be some number. DL is going to be some number, right? So for example, this is going to be X over square root of 17 squared minus X squared. You see, both sides of the equations are now just a function of X. It's just some sort of a graph. And what this says is, give me an X that satisfies both of these equations. So the way to find this X is to plot the right-hand side. It's going to be some kind of a function. So, right, so this looks like some sort of a thing, okay? And you plot the left-hand side. Now, the left-hand side can either be a tangent of x over 2 or minus cotangent of x over 2. And you see, I will show you the graph, but I want to show you the schematic. So it's going to be something like that, or something like that. And this is all a function of x. We will see that we will not need the negative values. Okay, so we have cotangent of x over 2, some kind of a graph. You have a tangent or minus tangent of x over 2, some kind of a graph. And you have this right-hand side, some kind of a graph. You graph all these things. So now I will show you what these look like for several values of DL. You see, the only thing that controls the only control knob that you have is adjusting the value of DL. For example, by adjusting the well depth or adjusting the well width or adjusting the mass of the particle that's inside the well. So all the physical parameters like M, U naught, L, that all goes into the DL, script DL. And that's your control knob. So you can think of this as DL, you can think of this DL as a control knob. I think control has one L. As a control knob. And now I will show you what happens as you tune this control knob. Okay, so that's what these graphs look like. Let me make them a little bit bigger for you. Now KL is what I call X, right? So this is X. So what am I plotting? The blue right here, this is cotangent of X over 2. The black is minus the tangent of X over 2. It's a periodic function. And these other things, I had a wrong kind of shape. These other things, these other looking things are this right-hand side. So the right-hand side is basically X over the square root of some number minus X squared. So if you actually graph this kind of a function, it will look like this. And the shape of that thing, well, the shape is the same, but the exact form of that function depends on the control knob. It depends on this DL. So the red one here, this is right hand side, meaning this X over the square root blah, blah, blah. For DL equals 100. DL equals 100. Large DL. The burgundy, let's see if I have such a color. This is my closest that I can find. And this one is right hand side for DL equals 20. And I guess this one is, let me switch colors. I just changed the color. And this one is right hand side for DL equals 5. What does it all mean? I can increase DL by increasing U naught, by making the well deeper and deeper. I can increase DL by increasing L, by making the well wider and wider. I can increase DL by increasing M. So what this says that X is a value that satisfies these equations. In other words, X is such a value of KL, is such a number that corresponds to these intersections. You see, so these values right here are the allowable values of X, depending on depending on DL. So for example, if DL equals 20, so if I adjust the well width, well depth, mass, DL is fixed, then X is a number, it's a value, it's a real number that satisfies the intersection between this middle function and all of these tangents and cotangents. So it can be this, 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 it can be this. Okay. Often students ask, why do you want us to graph it? Because that's what these equations say. That's what they mean. It says, give me an x for which the cotangent of x over 2 equals that right-hand side function. The orange right here is the right-hand side function, and the blues are the cotangent. Or it could also be minus the tangent, so we should throw in the minus the tangent for the mix. So wherever the right-hand side function equals either the cotangent of x over 2 or minus the tangent of x over 2, that's where at that value of x, at the x at which that intersection happens, these equations are satisfied. So this is called a graphical solution. What I'm presenting to you right now, it's called the graphical solution. So when you're given a problem, first thing you would do is you would calculate the script D or DL from mass, from U naught, from L, calculate that. You would graph the right-hand side, you would plot the right-hand side, and then you would plot all these cotangent of x over 2 and minus tangent of x over 2, and you would just look at it, and you would see it. First of all, you would look at how many intersections there are. There's going to be a finite number. And that tells you the number of possible values of k that are admissible. And since energy is proportional to k squared, it tells you the number of possible energies that are admissible. I will get to that in a second. And then you would actually read off the actual value of x, which equals to the actual value of KL. Now, L is some number, so it will give you an actual value of wave numbers that are allowed for the wave function inside the well. I will unpack this a little bit more, but I want to explain how this is done on a computer. Like if I want a precise value of x, okay, I can look at the graphs, I can look at functions, but how do I actually get the precise value to as many digits as I want? So here's how computers do this. So if you have some function, f of x and g of x, this is f of x, this is g of x, and this is x, independent variable. To say that I want the value of x at which these two functions are equal, or at which the two graphs intersect, is to say that really what I want is I want the value of x for which this function, it's a different function, equals 0. So I can plot f minus g as a function of x. And it will be something that crosses a 0 at some value. The way that this is done computationally is you provide an approximate guess to the computer. Let's say you guess that this is the value of x. The computer then calculates the error and it makes the adjustment. And if it overshoots, then it says, okay, so the actual solution is somewhere in between. And it tries harder and harder and it brackets until you get the number to the desired accuracy. There are other methods, right? So it can also compute the derivative. It can extrapolate based on that derivative. It can recalculate, it overshoot, then it can go back based on that derivative and so on. There are many methods. So this is called numerical root finding. This is how it's done in practice. In your homework, again, the first thing you would need to do is you would need to compute script DL. From script DL, you will construct this right-hand side function. You would look at the intersections of that right-hand side function with tangent and minus tangent and cotangent. You would identify the number of roots. Then you would read off the actual value of x at which those roots happen. And then if you want to be more precise, not just eyeball, you can engage a root finder in whatever numerical package you're going to be using to plot. So many of them, like Desmos or Mathematica, have things like find root function or something like that. And it will give you an actual value of x to some precision that satisfies those equations. Okay, so that's how it's done for this problem. Now, the next thing I want to explain is like, where does all this thing come from? Well, this says that there are discrete specific values of wave numbers that allow satisfaction of those four boundary conditions. Evidently, you cannot stitch those three parts of the solution for any wave number that you want. You can only do that for specific wave numbers. Now, your textbook has an excellent intuitive explanation for why that is, but let's consider, let me give you the following. So here are your two regions. Let's say you chose some arbitrary value of k, and here you just draw the graph. And you see, since we want to connect it smoothly to region 1 and region 3, it means that in region 3, it has to take off with a positive slope because the slopes have to be continuous. If it takes off with a positive slope, that means region 3 will have to have a mixture of growing and decaying exponential. Just decaying exponential cannot provide a positive slope. But wait a second, we're not allowed to have a growing exponential in region 3. So you see, you can already see that you cannot just take an arbitrary value of k. You cannot satisfy boundary conditions with an arbitrary value of k. And the same thing here. You cannot have something like this, because this says that this must involve a little bit of the decaying exponential coming in and joining region 2, but you're not allowed to have a decaying exponential. So it's possible to satisfy all four boundary conditions only for very specific values of k. And those are the values of k that solve these four equations. And we're just using x to simplify the equations, okay? That's what we're doing. So let me write down that the four boundary conditions can be satisfied for only very specific values of k or kl, x being kl. So, specific values of k also means specific values of kl. Okay, your textbook has a really nice, beautiful discussion of what happens if you don't fine-tune the value of k just right. That's what this math says. What about energies? Well, remember that the energy is given by h bar squared k squared over 2m. So I can rewrite that as, k equals square root of 2me over h bar squared, or we can multiply through by kl, x equals kl equals 2me times l squared over h bar squared. So that's the set of possible x's. So once you find the set of possible x values, that then gives you the set of possible values of E. So if you found the set of possible X sub n, X1, X2, X3, that gives you the set of possible E sub n. Okay, so perhaps I can just say that this is h bar squared over 2ml squared times x squared. So what I went here is I multiplied top and bottom by L squared, and this is it. So in practice, what you do is first you are given the parameters. You're given the parameters DL. When you know the parameters, I'm sorry, you're given the parameters M, L, U naught, the well depth, particle mass, and so on. And from that information, you calculate script DL. You construct those functions, you plot them, you look at them, you identify the number of levels, you calculate the actual values of x1, x2, x3 at which intersections happen, plug them into this formula, and boom, you get a set of energy levels. Okay, that's how it's done. I would like to draw your attention to one interesting fact. So in the infinite well, there were infinite number of levels. In a finite well, there's a finite number of levels. You see, if you look at this graph, you can see you only have finite number of intersections. For example, for DL equals 5, there are really only two solutions, two values of x at which the right-hand side equals either the tangent or the cotangent. That's it, just two solutions. Two values of x, meaning two values of energy. There's a finite number of levels. You will always have at least one level. So you see, as I make DL arbitrarily smaller and smaller, for example, by making the well shallower and shallower, you will always fit at least one level. But in general, you have more than one solution, but it will always be a finite number of solutions. So I would like you to understand that. So if I have a finite well, for a finite well, for a given value of U naught, M, and so on, you have a finite number of energy levels that fit inside. Okay, so for a given U naught, there is a finite set of E inside the well. So here's U naught. And in the next video, we're going to digest these results even further. If you want to see all the intermediate details that led to these equations, you can watch the optional video, okay? But I tried to redesign the lecture so that you can skip over those details and get to the meat, understanding how to do the calculation in practice, which you will need on the homework, and in the next video, reflecting on what all this means. Okay, I'll see you in the next video. Thanks.